Good morning, everybody. So this morning I will start out with more lectures on elementary hydrodynamical phenomena mostly and techniques. And I have made a slight change in my plan. I actually swapped the lectures 4 and 5 because I realized when preparing them that the sequence is probably more natural. So I will talk first more generally about gas dynamics, and then start with one numerical technique in the second half of this morning's lecture, namely smooth particle hydrodynamics. So before we get into things, let me maybe show you an old movie that I once made of a forming galaxy cluster that I want to show you here to illustrate you some of the coarser differences that you will see here in a few minutes between gas dynamics and between collisionless dynamics that I talked about yesterday. So in these 6 panels, you see different views of this cluster. And here it's simulated with dark matter and non-radiative gas dynamics. So ordinary ideal gas representing the baryons is simulated here as well as dark matter. And the dark matter density you see in the top left, the gas density in the top middle, and there's also the gas temperature field. This is something now you have for as thermodynamic quantity for the gas. And in the bottom, something that you can ignore, the thermodynamics and kinetics and moisture storage effect, as well as the ratio of the shocks. So as this runs and the cluster forms here, you'll see actually that the dark matter halo that's now built up is somewhat different from the gas structure. You'll see this in a little while more closely when the evolution is repeated from redshift 1 and a little bit enlarged on gas. Then the dark matter behaves quite differently from the gas in the sense that it's collisionless. The gas is smoother because of its collisional nature. You see this here in the gas evolution. As these satellites and smaller galaxies merge into the cluster, their gas distribution is relatively quickly dispersed. And you see interesting hydrodynamical phenomena here. Shock waves and contact discontinuities in these structures that move through the cluster. And that's what we are going to be interested in a lot. So, if you compare to the dark matter here, which was much more lumpy, the gas showed this hydrodynamical phenomena of shocks and contact discontinuity stripping, and also, as you see here a little bit, in the temperature field of fluid turbulence. And Ralph already alluded to turbulence. This plays a crucial role in particular in the interstellar medium, but not only there, also in the intragalactic medium, in the intracluster medium that we have here, but possibly also in galaxies, in the atmospheres of galaxies, and maybe even on slightly larger scales out to the perturbed intergalactic medium. So here you again see the dark matter to contrasting this extremely lumpy nature is because the dark matter lumps that fall in, they can only be destroyed by gravitational tidal forces acting on them. Basically at the edges they take off material, but otherwise these things can basically fly through each other because it's collisionless. The gas can't do that. You cannot put two gases through each other. The fluid moves with one given velocity at any given point in space. That's the fundamental difference that you can also infer from this movie. Now, let me start with a few slides on the basic equations of hydrodynamics. So the Euler equations for inviscid gas dynamics. Inviscid gas dynamics means that viscosity, internal friction in the gas is negligible. This is commonly called an ideal gas. It turns out ideal gas is the ideal gas model, which is really a model. This is not something that's realized in nature. Every gas is basically not an ideal gas. However, if a gas is very thin, if it's very rarefied, then its internal viscosity is normally very, very small and often very negligible. Turns out in astronomy and astrophysics, the gas densities we normally deal with in structure formation are actually rather low compared to everything that we have here on Earth. And so helium and hydrogen gas in the cosmos is really behaving like an ideal gas for the most part. So that's why this is a very good approximation often. And it has another a large number of consequences. Some of them I will mention what this means that the viscosity is so low. But for the equation of motion now, this is the equation of motion of the gas. The acceleration of the gas is proportional to the negative pressure gradient, right? You pushed away from high pressure. It's very simple. Okay, normalized to the density. So this is basically rho times the acceleration. This is the acceleration density, so to speak. And that's given by the pressure gradient. Very simple. Now this time derivative here is actually a convective derivative. This is correct if you are sitting on a fluid element. If you are a gas cell or gas atom or whatever, moving along, that's your equation of motion, right? It's a convective equation of motion. And if you want to put this to fixed Eulerian space, you have to take a partial derivative of time and then add this convective spatial derivative part. The second equation that we have in gas dynamics is the continuity equation. That describes how the gas density that you have around you changes as you move along. And this can very simply derive just from conservation of mass. That's nothing else what this expresses, the continuity equation. You then also have a thermal energy equation. So there is an internal degree of freedom in the gas, which is the thermal energy per unit mass, or in other words, the temperature. Right? So you have the temperature of the gas. And the temperature of the gas is changed by adiabatic work against the fluid element. If it's compressed, you do work against the pressure that this gas has, and you raise then its thermal energy. Right? You compress a gas, you make it hotter, and vice versa. So this is expressed in the thermal energy equation. This is a reversible process here. Right? So this alludes to reversible, and this is a distinction we'll also get to between irreversible and reversible processes. Then you have equation of state, which is actually relating the pressure that you get for the gas, which appears here, to, and also in the equation of motion, to the thermal energy per unit mass, to the temperature. So this is a constitutive relationship, a material property, and for an ideal gas it takes this form. The gamma is the ratio of specific heats, and most relevant is usually monoatomic gas, gamma of 5/3, and then also in this case the thermal energy per unit mass and the temperature are related like this. So they're always essentially the same quantity, modified by things like the Boltzmann constant and the mean molecular weight, mu, that's appearing here. So far so good. And that is almost, for most people would think, or in a sense, this is basically a complete set of equations you need now to start Lagrangian hydrodynamics for an ideal gas. There is one more conservation law actually. You can show that from these equations it follows that something, what we call the entropy, is also conserved. And the entropy, you can show this for the thermodynamic entropy or for some related quantity A, which I define here as the pressure over rho to the gamma, so-called entropic function. This is easier to work with this, and also this is often used in X-ray astronomy, something like this. This is directly related just by natural constants like Boltzmann constant and molecular weights, etc., to the real thermodynamic entropy, so it's often called the same thing. And this entropic function is actually constant. It's conserved, right? Which tells you in this equation you find out is indeed the case from these already. So that also means that what I've written here for ideal hydrodynamics, these Euler equations in this differential form, they describe an adiabatic flow only, where the entropy is constant everywhere. So we'll see later that this can't be the full story in a way, right? We basically know that the entropy, those of you who know about shocks will know that the entropy goes up at shocks, and this seems to be contradicting that, right? And it basically means that a shock is not really described by these equations directly, right? They break down at a shock at some level, which we'll see. You can also describe the Euler equations for ideal gas dynamics in a different form, in the Eulerian form, and you have to if you're confused about, sometimes you see equation of motions, and if you're unaware of this distinction, you think, wasn't this equation different? For example, here the mass conservation equation. Here is my continuity equation, looks like this in Eulerian form. And if we go back, we had here the continuity equation also. But you see that this advection part here, this is here the density is outside of the nabla operator, and here it's inside the nabla operator. Okay, the distinction lies here in the convective derivative, and these two equations are consistent, but the difference only that in one case I use the convective derivative, in the other not. Then the equation of motion takes this form, and here it's more apparent that it's really also a conservation law for, in this case, the momentum density. So the momentum conservation law directly is the equation of motion, and this takes this form in the Eulerian case. And similarly, the thermal energy equation is really basically an equation that ensures that total energy is conserved. And in the Eulerian case, this takes the form of an energy conservation equation. Or it's actually a continuity equation like the mass, right? You see these three equations have the very same structure, so-called hyperbolic conservation laws, because there are also continuity equations here for the momentum and for the energy. And there is the flux, this is the mass flux, this is the momentum flux, and this will be the energy flux. They always are in this form of a conservation law. And here you have a new symbol appearing, this E, little e here. This is now the total specific energy per unit mass, not only the thermal energy like that we had used in the Lagrangian form. Here it's more convenient to add in the kinetic energy per unit mass, and then you have the total specific energy per unit mass in these equations. Okay, so far so good. So these are the Euler equations. Now, there's also something called the Navier-Stokes equations. So the Navier-Stokes equations are kind of the equations of real gas dynamics, when you do not make this somewhat idealized assumption that internal frictional forces can be neglected. For example, if you look at honey, this is a very viscous fluid, still a fluid, but it has a lot of internal friction. It's hard to make it move. And there are, of course, also normal fluids that have a lower viscosity, say water or air. And those you can describe with the Navier-Stokes equation. They look like the Euler equations. Here, these are written in Eulerian form. In fact, they're the exactly same as before. However, there's something on the right-hand side here. There is an additional force, nabla times this capital pi, and then we have also additional work against these forces, source term, so that the balance of energy will also be fulfilled. So the work that appears here will then go into, that is taken out of the kinetic part, will then go into the thermal energy reservoir, for example. And this pi is called the viscous stress tensor. And the most general form of that this can take is this. It's a sort of a second rank tensor in the velocities, and there is a shear viscosity part and a bulk viscosity. So the bulk viscosity, there are two material coefficients, eta and this psi here, and they are determined by the material. So there's no deep theory. Well, there might be something from quantum physics or whatever, kinetic theory that gives you these coefficients, or from transport theory, but they describe basic properties of whatever fluid you have. How large the viscosity is. Those parameters could also depend on temperature or density and so on. Right? So the viscous stress tensor basically describes the internal stresses that make the fluid resist motion, basically. And this can be against compression or it can be against shear. And in practice, a very important special case is incompressible flow. Well, there are more distinctions. Normally, you can, for example, have fluids that have no bulk viscosity but only shear viscosity. This is a quite common case. For example, in a very hot plasma, you have something called the Perginski shear viscosity. This would be applied to gas in a galaxy cluster. And that would depend on temperature, but there would be no bulk viscosity. There would be a shear viscosity. But a special case that I mentioned is for incompressible flow. Then when you have incompressible flow, for example, this part bulk viscosity will be not there, right? Will be unimportant. You don't. And then you have the shear viscosity, but because of the incompressibility, a lot of other things simplify, and then you can summarize that and write the Navier-Stokes equation of motion in this form by defining also something new, the so-called kinematic viscosity nu, which is often done, which is the shear viscosity normalized over the density. This kinematic viscosity nu is, for example, the viscosity that appears in the definition of the Reynolds number that was appearing in Ralph's talk for turbulence, right? So this is kinematic viscosity, and if you then write the equation of motion, again in Lagrangian form, this on the bottom right is now the equation of motion in Lagrangian form, the Navier-Stokes equation of motion in Lagrangian form. You see this the same as in the Euler case, except that on the right there is this new nabla squared v, velocity. And this is exactly the only difference here. And you see then the nature of what this viscosity does very nicely, right? So it acts here like a diffusion term, trying to spread out sort of large changes, local changes in the velocity. And in this form, it's, for example, used in the theory of turbulence a lot. So then some brief comments about magnetohydrodynamics. This is yet another sort of more complex case of the ordinary Eulerian hydrodynamics. Here, consider a case where you now have basically ideal gas dynamics, but in addition, ideal magnetohydrodynamics. And the idealness here is that the conductivity of the medium is going to infinity. So it's if you have a perfectly conducting medium, what does that mean? Well, one thing it means, if you look at Ohm's law, that gives you the current density in response to the electric field and a magnetic field, then and if the conductivity goes to infinity, basic current density should go to 0 in this case of free charges, and so the electric field is basically then given by the B field in this form from this equation. And with this you can work on the Maxwell's equation and get rid of the electric field there and simplify Maxwell's equations, and you find out then that we should have an induction equation in this form, that the time evolution of the B field from Maxwell's equation is then given by an expression like this. And the other magnetic equation that is surviving is the so-called divergence constraint, div B equal to 0. Right? This is anyway one of the Maxwell's equations. We don't have magnetic monopoles. And so in ideal magnetohydrodynamics, we'll want to govern the dynamics of the magnetic field is governed by this equation. And in the continuum, if we start out with a magnetic field that fulfills this constraint, div B equal to 0, this will also stay like this forever then. Okay, we'll not create by chance then magnetic monopoles. And I just mentioned this. I will not talk much about numerical schemes for magnetohydrodynamics, but div B equal to 0 is one of the pains that numerical treatments of ideal magnetohydrodynamics have to deal with. Because once you discretize this induction equation, it does something. I mean, it does induction, and it does it probably reasonable for a while. But if you're not careful in this discretization scheme, after a while you violate this, start violating this, and then normally many schemes then become unstable and develop pretty unphysical magnetic field structures. Now, what else do we have to do ideal magnetohydrodynamics? So we have to add this equation to our Euler equations. But the Euler equations are also slightly modified. We have changes there that we now need to take into account something like a magnetic pressure term. So the gas pressure is enlarged by a magnetic pressure term, and then we need to replace the pressure basically with this total pressure. And also the local energy density, specific energy density, is modified with the magnetic field. So we now have a thermal component, a kinetic component, and a magnetic energy component in the total energy per unit mass. And these are basically two important changes. You have to replace the corresponding symbols in the Euler equations with this. There's still a small additional part there. In the advection part, there's also a magnetic term appearing here, both in the equation of motion and in the energy equation. And then these would be the equations of ideal magnetohydrodynamics. Obviously, now solving all of this numerically, there's a vast literature on how this is done. And we'll address some aspects of this in these lecture course. So then, let me talk maybe about shocks, okay? Now, a shock is something that is very important and interesting also. It turns out, even if you are taking these inviscid ideal Euler equations, and you, for example, consider a sound wave with some amplitude, high amplitude, and you let it evolve for a while, let it travel, you will, after a while, find out that if the amplitude is reasonably large to begin with, that this sound wave will change. It will modify. It will start to steepen. It's because at the top of a wave crest, the speed of sound will be slightly faster because the density, because it's compressed, the temperature is higher. So the wave sort of crest on top will move slightly faster than the rest of the wave. And that leads to a steepening of the wave with time. So when you start out with a nice sinusoidal wave, it will modify its shape, and it will tend to become steeper and steeper and steeper. And eventually you have, basically the front and the beginning, you'll have a situation where the top tries to overtake sort of the bottom of the wave, and the shape is not at all like a normal sine shape anymore. And so this is the phenomenon is called wave steepening. And then what will really happen before this wave breaks is that you develop discontinuities in the flow. So this is something that appears due to wave steepening already, but it also will appear if you run two fluids into each other at supersonic speeds, as we'll see. In both cases, a flow must develop discontinuities, an ideal gas flow. And you can see this basically by analyzing what happens at this generic situation, that you maybe have some small region, say this blue region here. This is, in this case, suppose some fluid is moving through this region from the right with a velocity v1, p1, rho1, and going out through the thin layer on the left with another state, velocity 2, p2, rho2. Now, if I make this interface very thin, very small, infinitesimal thin, you would say, well, then due to continuity, if the flow is smooth, these quantities must be the same as the quantity with the index 1, right, upstream. Just because of continuity, right? In a thin, extremely thin layer, nothing will change. Fluid properties must be continuous. But if you are making this, so this is certainly expected. And then the question is, can you actually expect discontinuity in all cases? And there the answer is surprisingly, or is essentially no. You can take the laws of energy, momentum, and mass conservation, and put a little box around this discontinuities and ask yourself, okay, when I ask, how much mass flux, energy flux, and momentum flux is going in from the right side and comes out on the left side, there this must be continuous. So what the continuity really must apply only to the mass flux, the energy flux, and the momentum flux. Because if I make this little box infinitesimally small, and these fluxes would be different, then it would mean that somehow mass accumulates, for example, in there, right? Or energy accumulates in this region. And that can't go on for a long time, right? If it can go on at all. So the continuity in the flow applies to the mass flux and the momentum flux and the energy flux. And just from this simple idea, you can then derive conditions on how these quantities must be related in all cases. If the Mach number of the flow, this is called in this upstream case, so in front of the discontinuity, we define a Mach number as the velocity of the gas relative to the sound speed in this region. And so if you then consider what happens at a discontinuity, you'll find out the so-called Rankine-Huguenot jump conditions, which relate exactly these upstream and downstream primitive fluid variables, the pressure, density, and velocity. You find out that basically the continuity of the conserved quantities mean that these quantities need to jump in certain flow situations. And these jumps are happening in the density, in the velocity, in the pressure, and in the temperature. And the size of these jumps is given by these relationships as a function of the gamma of the flow and the Mach number of the flow. So what we have here is that basically at a shock, when the flow develops this discontinuity, it will abruptly change its density, pressure, and velocity. And this is always, if you have a real shock, it will always be an increase in the density. What in a real shock happens is this continuity must develop if the flow is supersonic. If the Mach number is larger than 1 and you have this sort of shock region, that means that at the shock the flow is decelerated from a supersonic motion to a subsonic motion, and it's compressed in doing this. This is generically what happens in a shock. Right? In the rest frame of the shock, where this is fixed, the gas comes in and streams out on the other side. And this is like a big decelerator here, the shock. The shock is like a brake. It brakes the fluid from its dangerous supersonic speed to a more accommodating subsonic speed. That's the big brake. And in this braking, it actually also modifies the entropy of the flow. It puts some of the kinetic energy it's extracted into heat, and this is then irreversible. Actually, the heat that's generated is partially due to compression. The gas is decelerated at the shock and compressed, so that heats it up, and the other part is irreversible heat injection, which is related to entropy production. So that is basically what happens here in such a shock. And here are often such shocks are, don't want to discuss this in much detail, but they are often tested and studied in shock tubes. This is something that you would do in a hydrodynamical code when you are experimenting with maybe your new code and you want to see whether it can simulate reasonable fluid phenomena correctly. And here are 3 different time evolutions of so-called Riemann problems or Sot shock tube problems. This is when you put 2 of these gas phases. So basically you can make an initial conditions where you have an interface. You give the left state some velocity, some pressure, some density, and you give the right state the same. Then you want to see what happens. And this is an initial conditions problem, and so it's well defined, and you can then study what happens. And this is done in so-called shot tubes or some Riemann problems. Here on the left column, this is one typical Sot shock tube problem where you have the initial gas density was at rest. Density on the left was up to the middle, was 1, and here was much lower on the right. And then you let it run for a while and you get something like this. So the initial step evolved in a more complicated multi-step feature with some inclined slope. We will discuss more what this precisely is, in particular this inclined thing here is a rarefaction wave. But there is a shock hidden in here, and who knows where the shock is. In this particular case, it must be a discontinuity, right? So we have 2 possibilities. The 2 possibilities for a discontinuity is this jump here. So you see a black line which is underneath these blue points. And here is one jump in the black line. This is a real discontinuity, right? A real jump at one point of the density. And here's another one. So there are two candidates in this example for shocks. If you just look at the density here, But if you look at, say, the velocity, then you see that there's also a discontinuity right here. And then also in the pressure, there's one discontinuity only. So the pressure is continuous at this place and also velocity. And that's why this guy is not a shock. This is so-called contact discontinuity. Here the pressure is continuous. Okay, we'll discuss this tomorrow more, what this means. So, but I might want to make a little bit of a digression after this somewhat drier material on just equations, illustrate to you that this stuff is really important and very, very fundamental. And also with the jump conditions, for example, you can do real astrophysics in some cases, really, really interesting astrophysics. And I want to give you one specific example here. So now if you are looking at this man here firing off a bullet, you see that this flies through air, this bullet, with a supersonic speed. And then you have a so-called bow shock, because it's like a bow here in front of this supersonic motion. That kind of means that the gas here on the right, this is not aware of the fact that something is coming towards you, right? Because this information of this bullet coming cannot propagate more with a higher speed than the sound speed here. And it's only then the shock that hits you suddenly into the face, basically. That's what happens for this gas. And what's interesting is that such a bullet-like motion and such a shock is actually, right out there in the universe, visible. It's one of the most gigantic shock waves that we know. That's in the so-called bullet cluster. And here is the bullet right there. And this is a cluster where we think this bullet is a small cluster that has been shot through this parent cluster and has come out on the other side. Now, where is the shock here? This picture is kind of deceptive that you'd say, it's here. It's the strongest feature, but it's actually not there. It's over there, this fainter bluish edge. This is the bow shock. This here is the contact discontinuity, okay, which is behind the shock. And the bullet cluster, as many of you will know, is particularly interesting because it is one of the most convincing indirect, or direct if you want, proofs of the existence of dark matter. This is a press release image from NASA from a few years back, where in blue you see here the mass peaks inferred from gravitational lensing observations, and in red you have this X-ray emission. It shows where the baryons are. Basically, here's the contact discontinuity, but that's where the baryons of the bullet cluster are for the most part. And the important thing is that these baryons are displaced from the mass peak. And so that means that the baryons are not what's dominating the total mass in the cluster. So there is another mass component which is not the baryons. That is our dark matter right there. But so then there's more to this. So this is just another image that shows this better not in a press release version. This is the mass contours from weak lensing, and then here's it overlaid over the X-ray emission of this cluster. You see this displacement there. And the X-ray observers, they are doing cool things with this cluster. For example, you can look at the projected temperature profile through the system, and you see this, that ahead of the shock, the temperature is, in the parent cluster is something, it's this level, few keV, and then there's a real sharp rise to a very large temperature, and then a decline again to where the bullet is. This one is again cold. So you have here two discontinuities. One is interpreted as a shock here, and the other discontinuity that we saw in the temperature is the contact discontinuity. The cold material, you shoot the cold gas into this parent cluster, and this is a little bit hotter, the parent cluster, and then you have ahead of this bullet this shocked material, right, which is very hot. And then, but you can do more now with the Rankine-Huguenot jump conditions. You can, for example, look at the surface brightness profile of this cluster These are the observations here, and then you make a model that has this sharp shock feature in there that compresses the gas by some factor that's just given by the Mach number. And here the model fits this perfectly for a density compression ratio of 3. Right? And if you remember the formula for the jump of a shock in the density jump is directly related to the Mach number of the shock. So from this measurement, you can now infer the Mach number of the shock, which is 3 in this case, roughly. Now the Mach number tells you, however, the ratio between the sound speed in the pre-shock gas. This is at a temperature of 9 keV, so you know the sound speed there. And multiplying that sound speed by the Mach number 3 gives you then the speed with which this shock propagates into the cluster. Right? So that's interesting astrophysics, right? I mean, in cluster physics, you can directly apply these Rankine-Huguenot jump conditions. Yeah, so, but there, I don't want to discuss much of the science, but, about the shock velocity, whether this is then really the speed of the bullet. It's not actually, this identification is a bit premature. But I want to show you that if you then do simulations and want to understand, is it really true that we see here, say, a galaxy cluster merger or collision? And maybe can I confirm what the mass, is the mass model realistic? Do I get such a shock from the right collision? For example, we can make a model that was suggested in this mass modeling in the Clow paper. Maybe the parent cluster has a mass of 1.5 times 10 to 15 solar masses, and the bullet might be up to a factor of 10 smaller. So we give them, in a little toy experiment, the sizes and masses that you expect according to cosmological simulations, an NFW dark matter halo, with the gas placed in hydrostatic equilibrium into these halos at the cosmic abundance. And then you can let these two things fall together from infinity, so with a zero energy orbit, and see what happens. And let's take a look at this. Run a little calculation, which is quite simple. You can do in a half day or so. Now you see here the bullet going through. This is in X-rays on the top left. This will be a temperature map, and there you see the shock, the bow shock, getting now weaker, and then also the velocity field. And now, of course, what you now have to decide, you don't quite know at what time was the observation made, right? And apparently the bullet has already come out on the right side of the parent, but it's still in there, and maybe there, roughly there or so, right? Could be. And then you would say, this doesn't quite look like what I saw in the observations. Yeah, because the colors are different, right? Yeah, I mean, that is this is really the whole story, because if you put the same colors on this very same image, then it looks like this, right? Much better. So this is the simulation, and this is the observation, right? In fact, this reproduces, such a simple model reproduces all the primary features of this, what's observed in very, very good accuracy. Here, this is just to make this point. Here are the observations of the temperature profile. You see here the measured points going through the cluster, and the red line here, this is now a measurement from this little hydro simulation. Yeah, I mean, with zero fiddling, when I made this once, I was extremely pleased. Woo, it's amazing. It actually works. Little ordinary ideal hydrodynamics gives you this sort of level of agreement. And then also the lensing observations are reproduced. Now, to close off this little excursion into fundamental fluid phenomena in Eulerian gas dynamics, I want to briefly discuss fluid instabilities, because that's also, besides the shocks, this is another very important basic phenomenon. And unlike shocks, this fluid instability business only really appears in multidimensional flows. So this is generically something that is not trivially appearing if you just have a one-dimensional model, even though you can have a 1D shock. So for example, let's consider a situation like this, that we have a so-called shear flow, that along the x direction, this upper half of the plane supposed to have density ρ2 and flows to the right with velocity u2. And the lower half flows to the right with velocity u1. Sorry, this is actually suggesting flows to the left, but the sign convention here is also to the right for this velocity. Now the question is, okay, this gas will happily flow in this sort of shear when you have basically a tangent orthogonal to the flow direction. You have a change of the fluid speed. This is what you call a shear flow. So if u1 and u2 are unequal, then you have a shear flow. The question is, okay, what happens here? Well, normally nothing happens. So if this is a mathematically perfectly fully specifying everything that's there, and if the pressure is equal here, I identify this, but let's assume the pressure in both regions the same. So then you have basically a discontinuity here. Density are different. Pressures are the same. Density is discontinuity. But if the flow is laminar across this interface, then nothing really should happen. You can plug this into the Euler equation. That is what the dynamic equations tell you. Nothing should change. But what happens if you slightly perturb that, and that's what we've done yesterday in the hands-on session. We slightly perturb the interface, put in a little bump here on the road, or put in an explicit perturbation, like we've done also in our experiment yesterday. And this you can do to start instability analysis. You will put in a little perturbation, typically a wave-like perturbation, and basically do an eigenmode analysis and want to see what happens if I make this ansatz of a small exponential perturbation. What happens to it? Will it just oscillate? And if it's or will it maybe grow? And I see that whether it's oscillating or growing by plugging in this small perturbation into the Euler equations. Then you do a whole lengthy analytic calculation and derive Bernoulli's theorem and other stuff. You know, it's 1 or 2 pages of algebra. And then you arrive at a so-called dispersion relation. And I don't want to go now through this algebra. This dispersion relation looks like this, also still a pretty lengthy expression. Right? Also, what I didn't mention was that for the fun of it, let's also put a gravitational field here in the c direction. Okay, the gravitational field needs to be compensated then by some suitable pressure gradient if you want to be in hydrostatic equilibrium, and that we assume has established. So this gravitational field is still here with the g, right? So and then we get this sort of dispersion relation relating our omega in our exponential with the wave vector k. What does that tell you now? Well, it tells you basically how the frequency and the wavelength of these waves are related. And for normal traveling waves, this omega would be a real number. Okay? But what if this solution of this equation is imaginary, particularly if it has a positive imaginary part? You plug this in here, and then you will get exponential growth. Right? So if this dispersion relation has imaginary solutions, we'll see that, well, it will trigger instability. Right? This is sort of how this is derived and analyzed. And from this, we'll then also have the growth rate, right? Because we'll then have the exponential growth. So dispersion relation will also give us the growth rate if it's unstable. And now there are some special cases. For example, of this formula, the Rayleigh-Taylor instability is quite well known. So that's the simplified case if there's no shear flow present. So that means the U1, U2 is 0. The fluid is at rest. If it's at rest, then the dispersion relation simplifies to this expression. And that means if the ρ1 is larger than the ρ2, then omega squared is positive, and then there are no imaginary solutions, and everything's stable. Or in other words, if the lighter fluid is, now yeah, it's supposed to, yeah, I did this last night. Flow is stable if the lighter fluid is on top, not unstable. So we should change this. Okay, right there. Okay, sorry for this. Yeah, so we basically have here a situation. If the lighter fluid is on top, so if rho 2 is smaller than rho 1, then the lighter fluid is on top, the denser one is on the bottom. Then you have a stratification, okay, which is stable, right? If it's the other way around, then you get imaginary solutions, and then you will be unstable to so-called Rayleigh-Taylor instabilities. And it's kind of intuitively clear, if you put a heavy fluid on top of a light fluid, then you can extract potential energy. That's the source of free energy. Then the fluid motion can tap to create motion, right? It was at rest. To create motion, you need some energy, and this comes from the potential energy. The heavy fluid wants to go through the lighter fluid, and the lighter fluid is now, just to deceive you, is the dark fluid. Okay, but that wants to go up, and this is a phenomenon called buoyancy, basically. Right? So you're then buoyantly unstable, and then you get the characteristic mushroom-like things in the beginning, right, that grow up here. And these are the characteristic motion, this is the characteristic onset of the Rayleigh-Taylor instability, shows this mushroom-like feature. Then the other case that's also simple is the Kelvin-Helmholtz instability that we yesterday already looked at. There, the common case that we should look at first is when the gravitational field is 0, then the dispersion relation becomes this expression. And here you now have an interesting thing, that actually there are always imaginary solutions. They are always there, because provided there is a velocity difference. So that means any shear flow is unstable. Okay, if there's a real jump in the velocity, it's always unstable. If you don't have a gravitational field, at least, it will always be unstable. In fact, the small wavelengths will grow fastest. So the Kelvin-Helmholtz instability is really very, very efficient in destructing shear flows. But there is one case that you can stabilize a shear flow, for example, by a gravitational field. So if we have a gravitational field, the story is different. We'll have to look at the full dispersion relationship, and then you find that, okay, you will have stability if, in this case, the lighter fluid is on top. Okay, well, you want to have this, otherwise you're Rayleigh-Taylor unstable, okay? So you need for stability, you need that the stratification of the density is now in line with the gravity. And then secondly, that the velocity difference is not allowed to be too large. So if it's small enough, this condition is true, then this will have only real solutions, and then you're stable. That means with a gravitational acceleration, you can stabilize against the Kelvin-Helmholtz instability. And that's in a similar phenomenon you have now, for example, in a shearing gas disk. Okay, it's based on centrifugal acceleration, and there also you have modifications of this dispersion relation that will give you stability in certain cases, right, and suppress it to some extent, even though there is differential shear. And well, to close off, I mean, these sort of Kelvin-Helmholtz instabilities you actually see in nature sometimes. I mean, I haven't seen such cloud formations myself yet, but they are appearing, and some people take photos. There are hundreds of those. You see them basically in clouds, or here are two rivers that stream together, and if you enlarge this, you actually see here Kelvin-Helmholtz billows developing quite nicely. So that is certainly relevant, not only in astronomy. So I want to now stop here for about 10 minutes, take a break, and then we continue with smooth particle hydrodynamics. And also, if there are any questions now, let me know. Yes, please.
So I'm wondering when you show the movie of this bully cluster, and I will expect when bully shock into this, then you will develop the sort of instability behind the shock, because the shock decelerates. But I didn't see the fluid instability occurs in the in the contact discontinuity part of the shock.
Yeah.
So it's due to resolution of the.
Yes, I mean there is. It's true. There can be. So, which instability precise you meant? You meant the Kelvin.
Because the reverse shock and the slowdown level should be radical instability. And this contact discontinuity part.
Yes. Yeah, that is. I think you're right. But the resolution, indeed, of this calculation is not very large. So this was done with smooth particle hydrodynamics. We'll talk a bit later about the problems with this method. It's relatively viscous method. So it tends to wash out a lot of the more subtle fluid features and can prevent especially the onset of fluid instabilities that way. And that is probably also what happens here at some level.
So this one is from the Gaussian simulation?
Yeah.